Okay, now let's talk about area and arc length. In the earlier sections in Cal 1, we defined the area for curves by using rectangles, and then we summed up infinitely many rectangles to find the area using integration. With polar coordinates, we can kind of do the same thing. But what we're going to do, if you look over here at this curve, if we want to find the area, span from theta equal A to theta equal B here of this curve, r equal f of theta, if we want to find that area, we divide that span of space into these little a bunch of these little fan wedges, and when you add up these wedges, you get an approximation for the area of the curve that's spanned by that curve. So between theta equal A and theta equal B. And when we integrate, it actually adds up infinitely many of those, and so the limit actually becomes the actual area. So the formula for this is the area of a fan-shaped region between the origin, the curve r equal f of theta, and theta equal A and theta equal B, which is what we have up here. To find that area, we actually would use this formula, 1/2 r squared d theta from A to B. So basically we just have to integrate from theta equal A to theta equal B, 1/2 r squared d theta. Now remember, r is f of theta. And so just a note here, the dA for area is 1/2 r squared d theta, which is the same as 1/2 f of theta squared d theta. Okay, let's take a look at a region here. This says find the area of the region in the plane enclosed by the cardioid r equal 1 plus cosine theta. So basically what I'm looking for is the area in here. Okay, well, if you graph a cardioid, you know that as you graph it, as theta goes from 0 to 2 pi, it sweeps out the cardioid. So what we're going to do here is we're going to use that formula where f of theta is 1 plus cosine theta, and then theta is going to sweep from 0 to 2 pi. And so, once you get the integral, you should know how to integrate the problem, but I'll go ahead and walk you through some of it here. So we'll square this binomial 1 plus cosine theta, and we get 1 plus 2 cosine theta cosine squared theta. I move the 1/2 on the outside. Well, then we can write cosine squared theta as 1 plus cosine 2 theta over 2. And then if you break that up into 1/2 plus cosine theta over 2, you can take the 1/2 and add it to 1 and get 3/2 here. So we have 3/2 plus 2 cosine theta plus cosine 2 theta over 2. And then we're still bringing the 1/2 down. And then when we integrate this with respect to theta, we get 3/2 theta. This integrates to 2 sine theta. This one integrates to sine 2 theta over 4. And then remember, we're evaluating it from 0 to 2 pi. And so when we evaluate it from 0 to 2 pi, at 2 pi we get 3/2 times 2 pi plus 2 sine of 2 pi plus sine of 2 pi over 4. Well, these terms are going to be 0 at 2 pi. And then over here, everything's going to be 0. All three of these terms are going to be 0. So basically what you're going to have is 1/2 of the 2's are going to cancel, so you're going to have 1/2 of 3 pi, or 3 pi over 2 for your area. So that's the area of that cardioid. Now this one says find the area of the smaller loop of the lemicon r equal 4 cosine theta plus 2. Now that means we're looking for this area here. that's in here. Now we can see the symmetry here though, so we don't really need to we can actually just get the area of the top piece and then double it. So let's go with it at that route. Now if you set r equal to 0, you actually will get you actually can get that cosine theta is -1/2, and so r is going to be 0 at 2 pi over 3 and 4 pi over 3. So the loop is actually swept as theta travels from 2 pi over 3 to 4 pi over 3. But due to the symmetry, we can just go halfway between them and go 2 pi over 3 to pi to get the area of the upper half of the loop. So let's go ahead and do that. So we're going to go from 2 pi over 3 to pi. Now remember, that's going to just give me the upper half. So what I want to do is, at the end, I want to multiply that by 2. So let's see what we're going to get there if we do that. Okay, I did a couple things here. So let me just tell you what I did here. First of all, 1/2 times 2 is actually going to cancel. So I canceled that out. Now you might be wondering, well, where did this 2 squared come from? Well, you can factor a 2 out of each of these, but remember it's squared. So what you're really doing is you're factoring 2 squared out. So you're really factoring a 4 out of that. And now it just makes this easier to square. So you have 2 cosine theta plus 1 quantity squared. Now if we square that, we get 4 cosine squared theta plus 4 cosine theta plus 1. And then I went ahead and moved the 4 outside the integral here. And now 4 cosine squared theta, 4 cosine squared theta plus 4 cosine theta plus 1. 4 cosine squared theta can be written as 2 plus 2 cosine 2 theta. And then we have the 4 cosine theta plus 1. And then if we add the 2 and the 1, we get 3. So we can do that. Let's see, 2 plus 1 is 3. So I have 3 plus 2 cosine 2 theta and then plus the 4 cosine theta d theta. So now if I integrate the 3, I get 3 theta. If I integrate the 2 cosine 2 theta, you're actually going to get sine 2 theta. If you integrate the 4 cosine theta, you're going to get 4 sine theta. And don't forget you've got a 4 out here tagging along. So we integrate this from 2 pi over 3 to pi. And so if we evaluate each of these at pi, well, these terms are going to be 0. And so we're going to get 3 pi here. But when we evaluate this at, let's see, what are we evaluating? We're evaluating it now at 2 pi over 3. So 3 times 2 pi over 3 just gives you 2 pi. And then we have sine of 4 pi over 3, because it's sine of 2 theta. And then we have 4 sine of 2 pi over 3. So you might want to check my trig here, but let's see, I got 2 pi minus square root of 3 over 2 plus 4 square root of 3 over 2. And so finally, let's see, so I get 3 pi minus 2 pi. I combined these two and got 3 square root of 3 over 2. And then you have 3 pi minus 2 pi in here, so that's just pi. So I have pi minus 3, let's see, pi minus 3 square root of 3 over 2. And then if you distribute the 4, 4 times pi is 4 pi. And if you multiply it here, 4 times 3 is 12. 12 divided by 2 is 6. So you get 6 square root of 3. So 4 pi minus 6 square root of 3 is the area of that inner loop. Now, if you want to find the area between two curves, you use a similar formula, but you're actually going to subtract the area of the outer curve minus the area of the inner curve, where R2 is the radius of the outer curve and R1 is the radius of the inner curve, and you just subtract the two. So this is similar to what we did with Cartesian coordinates, where we took the higher function minus a lower function when we integrated. And if you simplify that, it actually turns out that you can write it like this, where you're integrating from a to b 1/2 r2 squared minus r1 squared d theta, where r2 again is the curve that's farther out and r1 is the curve that's closer in. So let me give you an example of this. All right. Suppose we wish to find the region outside of the curve r equal 1 plus sine theta, and that would be this blue curve over here. Okay, and then inside the curve r equal 3 sine theta, that's that orange circle over here. So basically I'm looking for the area that's in here. Well, if you set these two equal, you can find that they intersect at pi over 6 here and 5 pi over 6. So what I want to do is I want to sweep my integral from pi over 6 over to 5 pi over 6. And when I do that, I'm going to have the outer radius is actually going to be the blue curve, and the inner radius is going to be the orange curve as I sweep from pi over 6 to 5 pi over 6. So what I'm going to have the, let's see, oh, I'm sorry, I said that wrong. We want the area outside of the blue curve and inside the orange curve. I apologize to you for that. We want this area. Gotta read carefully. Okay, so now let's back up and say that again. So the curve farthest out this time is the orange curve, which is 3 sine theta, and then the one closest to the origin is the blue curve, which is 1 plus sine theta. So using the formula, we integrate from pi over 6 to 5 pi over 6, 1/2, and then you take the outer curve, which is the 3 sine theta quantity squared, minus the inner curve, which is the 1 plus sine theta quantity squared. Now I'll let you worry about integrating this. I just wanted you to see how to set up the integral there. Okay, let's do one more. Find the area of the region that lies inside the circle r equal 1 and outside the cardioid r equal 1 minus cosine theta. So inside the circle would be, this orange region, and then outside the cardioid, that would be here. So we're really looking for this area here. Okay, so basically what we got to do is we got to find where we're going to sweep from. So we're going to actually sweep from minus pi over 2 up to pi over 2. So that will give us that area if we go minus pi over 2 to pi over 2. And then the one that's farthest away from the origin is, again, this orange one, which is 1, r equal 1, and then the one closest to origin, of course, is 1 minus cosine theta. So basically, we integrate from minus pi over 2 with 1/2, 1 squared, minus 1 minus cosine theta squared. And I'll let you go ahead and go through the arithmetic here, but eventually I got down here and got 2 sine theta minus theta over 2 minus sine 2 theta over 4. And when I evaluated that from minus pi over 2 to pi over 2, I actually got the area of 2 minus pi over 4. And again, the hardest part is probably setting up the integral. Even though evaluating the integral takes a bit of work, you should be a pro at evaluating integrals at this point. So you can freeze the video if you need to and work through my math. If I made an error, let me know. But anyway, just see if you can get the answer that I got, 2 minus pi over 4. Now the second half of this section, we're actually going to do it on another video, and we're going to talk about how you find the length of a polar curve. So we'll shut the video down here, and I'll pick back up on the next video.